So in order to come up with a different mathematical formulation of this basic idea of modeling the flow, we will first define what we will call a stochastic adjacency matrix M. And then we will express everything in terms of linear algebra, in terms of basically the ranks and this matrix M as vector matrix multiplications. And we will later see why this is good, because we will be able to start using the linear algebra tools to implicitly solve this system of equations that I showed on the previous slide. So here is how we proceed. Our goal is to define this stochastic matrix M that will basically be an adjacency matrix, which basically means we want to take the graph and represent it as a big matrix of values. And the idea is that if a page I points to page J, then we will have a non-zero entry in the cell Ji, and if the page J does not point to page I, then we will have a zero entry there. So now the question is, what is the value of the non-zero entry in the cell of the matrix? So the idea is if I points to J, then the corresponding entry Ji in the matrix M, it will be 1 over the out degree of the source node, so out degree of node I. Here you already see what kind of where we are going, right? Before we said that whatever is the importance of a node, this importance gets evenly split along all of its outlinks. So this means that all the outlinks of node I will have the weight 1 over di. So this means that our matrix is called column stochastic. This means that every column in our matrix sums to 1. Okay? So now that we have the whole graph represented as a matrix, we can also take all the PageRank scores of nodes and represent that as a vector. Okay? So the way we do this is that we think that we have one entry in our vector per page. We can think that our pages are numbered 1, 2, 3, 4, 5 up to n. So we have a vector of length n, and every entry in this vector basically corresponds to the PageRank score of a given page. Okay, so that is all good. And the other thing we know from before is that the sum of the entries of our vector equals to 1. That was the constraint of the flow equations we had on the previous slide. So now what is interesting is that we can take our flow equations, kind of our basic equation, and write it as in terms of the matrix M and the vector R. So we can write it as rank vector R equals the matrix M times the vector R again. So now we basically have a big system of equations, right? M is fixed, and we want to figure out what are the values of R. So just to convince you or demonstrate why we can take our initial flow equations and express them into this vector matrix product, this may not be obvious. So here is how we can understand that what we are doing is actually true and correct. So the idea is the following, right? Imagine that I have my matrix M here at the bottom, and I have my vector R, and now I'm multiplying M times R. And just for the sake of the example, let's assume that page I has the degree, out degree of I equals 3, and it also points, which means it points to 3 other pages, including J. This means that for a page I, the ith column of matrix M will have 3 non-zero elements. Here are indicated by squares. And each of these 3 non-zero cells will have a value of 1/3, right? 1 over the out degree of node I. So now imagine what happens when I take the jth row and multiply it with the vector R. When I'm scanning across the row here and I'm scanning down the vector R, I'm basically computing the PageRank score of node J, right? The PageRank score of node J is the sum of the importances that are stored in R times the out degree of that node that points to J. So this way, basically, we take this initial equation that we had before, and we express it as a vector matrix product. So now we basically took our flow formulation of the problem and expressed it as this recursive, in a sense, matrix equation that R equals M times R. Now, what we observe is that this looks very much like a kind of eigenvalue or problem. So let me just remind you what are eigenvalues and eigenvectors of a given matrix. Right? So if I have a matrix A, then X is called an eigenvector with the corresponding eigenvalue lambda if X is a solution to the equation A times X equals lambda X. Okay? So just saying it again, A is a matrix that we are given, X is something that we'd like to compute, and it's a vector, and lambda is also something that we'd like to compute and is a scalar, is a real number or a complex number. So the point being is that X is an eigenvector, Y is an eigenvalue if they are solution to this equation AX equals lambda X. So in our equation looks very much similar. Like we have M times R, which is the same as kind of A times X, and then we say equals R, and before we had equals lambda X. So what this means is that rank vector is an eigenvector of the stochastic web matrix M. And another important fact is that it is a principal eigenvector, which means that it corresponds to the eigenvalue with value 1, right? So here I can think that I implicitly multiply by 1 and my lambda is 1, right? In fact, the largest eigenvalue of M is 1 exactly because M is column stochastic. Why is that the case? That's the case because vector R has a unit length, meaning its coordinates are non-negative and they sum to 1. And each column of M also sums to 1. So M times R will be at the value of that product, of that dot product, will be at most 1. So this means that the corresponding eigenvalue, the largest eigenvalue of our matrix is 1. Okay, so what did we do now? So far we took our graph, represented it as this big matrix, and we reformulated our flow equations into this matrix formulation, and now we establish the connection between the matrix formulation and the eigenvalues and eigenvectors of this matrix M. So what this now means is that basically instead of thinking of this as solving a system of equations, we can think of our problem as finding the eigenvector of matrix M. And actually, there is a very efficient method for finding eigenvectors of a given matrix. And this method is called power iteration. So now we actually know how to compute PageRank. The way to compute PageRank is to find the eigenvector of matrix M that corresponds to the eigenvalue of with the value of 1. So that's what we learned so far. So now we can actually go and compute the thing. So let me show you what we have so far. We have our little graph, web graph on 3 nodes. We have our flow equations. And we also now can write what the structure of our matrix M. Here is the structure of our matrix M. Notice that the matrix is really column stochastic. So now how we can think of our flow equations, we can think of them as this vector matrix product, right? So R equals M times R.